Welcome to Unit 10. You should be reading sections 3.4 and 3.5 in your textbook prior to reviewing this slideshow. Unit 10, we're going to look at pretty much one topic, developing the structure of the atom. We'll go back and realize that in Unit 9 you found out there were a series of experiments that suggested to us that there were small negative particles that were common to each one of the elements. And in addition, we found out that there were small positive charges that were a part of each one of the elements. And it turns out that those negatively charged particles all had the same properties, mass, charge, ratio. Those were all the same. The positively charged particles had different masses depending on which element they came from. So where are we in the early 1900s? In the early 1900s, we knew about positive particles, we knew about negative particles. We also had some suspicion that there was some sort of a neutral particle inside of the elements as well, inside of the atoms of the elements as well. One of the things that we had determined was that, contrary to John Dalton's initial atomic theory, the atoms are not indivisible, but they're made of smaller, very similar types of particles. At this point, the electron, which you've heard of, is a negative charge, a small particle, was pretty well characterized. We knew its mass, we knew its ratio, and there's also the idea that the positive counterpart was also known. The big question is, if this is true, how are all these things put together? A man named Ernest Rutherford devised an experiment in the early 1900s that shed some light on what this arrangement of particles looks like in an atom. Rutherford did what's called a scattering experiment. My understanding of this is actually that he was using this experiment to show a couple of, like a postdoctoral student and another lab worker, how the equipment worked, and actually came across a pretty important discovery. So they set up the apparatus shown in the lower right-hand corner. The big boxy-looking thing, the cube, is a source of what we call alpha particles. The biggest thing for us to know about alpha particles right now is that they're fairly heavy on the atomic level, and that they have positive charge. Matter of fact, they have two positive charges inside of them. So the idea was we would take these big old heavy positive alpha particles, we would bombard a piece of gold foil shown in the middle of that ring with those alpha particles, and we would find out what happened to the alpha particles afterwards. If a gold sheet was solid material, everything all the way through, you might expect that the alpha particles would be bouncing back. If the gold foil was mostly empty space, you'd find out the alpha particles kind of went straight through. So his idea was, well, let's see what happens when we do that. What he found out was that most of the alpha particles went straight through the foil undeflected, okay, which means that mostly we're looking at empty space inside of the gold foil. But some of the alpha particles rebounded nearly straight back. I've read an analogy that's similar to hitting a piece of Kleenex with an artillery shell and having the artillery shell come straight back. Not what you would expect. If you want to see it work with a simulation of this, you can go to the link shown on the screen. Those are called PhET tutorials. Click on the Run Now button or download the file if you'd like to. You can turn on the electron gun by clicking on the number in the red circle over on the left-hand side. You can change the energy of the alpha particles coming out. How fast are they coming out, basically, is what you're going to change. And you can also change the size of the atom that's in the chamber, okay, by using the appropriate slider you have over on the right-hand side. So we kind of predate things here a little bit because we haven't talked about the atom that much itself, but think of it as just a small unit that we're going to see. And so in the next slide, I offer a couple suggestions, questions you might think about by using the simulation. And again, you don't have to do this. This is just something that's fun, so you might as well do it. So a couple of questions that come out is, one is, do the nuclei that you have in that gold foil, do they affect the path of the alpha particle more or less when the alpha particles are at higher energy? So take and crank up the energy in the alpha particles, watch what happens. Do they go straighter, or are they deflected more as they go through? Second thing you might look at is keep the number of neutrons. We haven't talked about neutrons much yet, but those are a positive particle that we've found in the end. They were suspected by the early 1900s, but they weren't actually discovered until 1932. But keep the number of neutrons fixed to some number and increase the number of protons. Okay. while keeping the alpha particle energy constant. So we're going to have the same stream of alpha particles coming out. It'll just make larger atoms, more protons in the atoms as we build different elements into that foil. So the question is, as the number of protons increases, what can you say about the approach distance of the alpha particles to the nuclei? Do they get closer? Do they go further away? Do they remain the same? The third thing you might think about is keep the number of protons fixed at some number and increase the number of neutrons. So what we're doing in these three questions, one is changing the energy of alpha particles, the second one is changing the number of protons, the third one is changing the number of neutrons. As the number of neutrons goes up, what can you say about the approach distance of the alpha particles to the nuclei? Do they get close? Does it go up? Do they get closer? Does it get smaller? Does it stay the same? Don't look at the next slide until you look at the simulation, because I give you the answers over there in the next slide. The question is, the nuclei affect the paths of the alpha particles more or less as the alpha particles go up in energy. What you'll probably find is as you increase the alpha particles to higher energy levels, they're less affected by those atoms. They're less affected. It's kind of like throwing a ball at something and a car going down the road. It's very easy to change the direction of it. If you just had to push on it and change it, it would be easier to change it moving slowly than it would be if it were moving very fast. Second question, we keep the number of neutrons fixed, we're going to change the number of protons that we've got. So keeping the alpha energy constant, what happens there? So increased number of protons, what you're going to find happening is that the alpha particles are repelled more, which means they curve more, given the same energy to start with. In the third case, when you look at the number of neutrons, while keeping the alpha particle energy constant, as the number of neutrons increases, you don't really see very much of a change at all. Okay. So Rutherford saw this. He saw this in these types of experiments that he did. So what's the conclusion from that? Well, most of the atom is empty space, and that's evidenced by the fact that most of the alpha particles go straight through the foil. The second conclusion is that since some of those alpha particles nearly came straight back, there are concentrated regions of positive charge with a high mass inside of the atom. So as you look at the picture down the lower right-hand side, you'll see I'm still in a picture that shows you centers or strong localities of positive charge, little gold parts inside that picture. And then when Rutherford looked at all this and put it together, what he determined was the best picture of the atom was that we had small positively charged particles surrounded by mostly empty space, pretty much like the picture over on the right-hand side. You should take the self-assessment on Unit 10. Unit 10 material will be covered on quiz number 3 as well as the midterm and the final.